Okay, so our next topic is meter bridge, and you also learned this in theory that meter bridge works under the principle of Wheatstone bridge. Wheatstone bridge, it works under this principle. So the Wheatstone bridge circuit is like this, and here we have to apply some potential difference. This is obviously in your theory, and here we attach a galvanometer over here. This resistor we call PQ. Okay, let's call this R, and this is S. Okay. So yeah, this in the theory. So here, as we know, that if we apply a potential difference over here, and these resistance are in ratios, okay, so we know that it works on this principle that if P by Q equals to R by S, if this is valid for a particular values of resistance, suppose you have 100 ohms over here, you have 200 ohms over here, and suppose you have 400 ohms over here and 800 ohms over here. So you can see that the ratios are in 1:2, that is 1:2 over here. So if in this particular case, if we have the resistance are in ratios, then the potential difference between this point, I am naming the point A, and this point will be B. So the potential difference between A and point B will be equal, and if it is equal, then there will be no current flow through this path. And from this we can be surely say that the galvanometer will not deflect if there is no current flow through this path, obviously. So this is the Wheatstone bridge circuit that works under the principle of P by Q equals to R by S. If these are equal, and those are in equal ratios, so there will be no current flow through this, and eventually we will get no deflection in the galvanometer. So here is the Wheatstone bridge circuit that I have drawn it separately, so that I can get a space over here to draw the meter bridge. So I will show you after this theory part. A meter bridge is actually a bridge. It's not a bridge actually, it's a piece of wood, obviously. It's a 1 meter wooden bench, and on this bench we have these metal plates over here. We will see that we have some metal plates over here like this, and we will get some bolts to connect some wires, okay, and here is a long wire, and we have also a connector over here and a long metallic rod over here. I will say this wire rod. So we have a rod over here, metallic rod, but right now I am not drawing it. Okay, and so this is it. And we have some connectors over here to attach the potential difference over here, to provide some potential difference. So see, this and this are the same thing, but they have different structure, obviously. So what is this for? See, this wire is actually a resistance, okay. It has some high resistance, that means obviously more than copper. It is made of manganese. So it has a resistance of like 2.4 ohms, and it's of 1 meter. So that's why the bridge is called meter bridge, because the length is 1 meter, and it has a resistance of this. So this wire actually contains both the resistance R and S over here. So this wire will actually contain both the resistance R and S over here. But I am not giving a mark. up to which part it will be R, from where it will be S. I am not giving that part, I am not dividing this resistance. So this combination, this where is actually a combination of R and S. Okay. And here we have two gaps to attach some unknown resistance. So I am just giving a resistance over here. Suppose this is unknown. And here we will have the known resistance. Okay, I am writing this known resistance as RB, that is resistance box. I will show you that on. So this is a known resistance. Just consider that this is a known one. Okay, this is a known one, this is an unknown one. So what we need to do is, we need to calculate the value of this unknown resistance. Okay, so how to do? This is our configuration. As I told you, here we have two gaps. This is unknown, this is a known resistance, the two gaps, and this is a combination of both R and S. So as you see the diagram there, we have a galvanometer here connected, where I don't know. So I am just leaving it up to here, I am just not giving the arrow over here. So we have a galvanometer connected to this point. And we have to apply some power supply, that is a potential difference between this P and R. So this is our P and this is our R, these two resistances over here. So between P and R we need to apply the power supply between P and R and Q and S. So between P and R we are applying a potential difference or the power supply, and looking this point, you see R and S and P and R. I have added power supply or potential difference across this system, and so this is our system. Okay. So now, as I told you earlier, that the condition of working of this principle, of this circuit, is P by Q equals to R by S. So if this is valid, there will be no current flow through the galvanometer or this. Okay. So what we do actually, we can connect this galvanometer wire to any point on this wire. Any point on this wire. Suppose if I connect this point to here, and at this point I get another point, means at this point after connecting the galvanometer I see that there is no deflection in the galvanometer. So from here we can easily understand, okay, for this particular point there is no current flowing through the galvanometer. That means the resistance R and S is actually this and this. P is this and R is this. So for this configuration there is no current flow through this galvanometer. That means P and P by Q equals to R by S is obeyed for this particular situation. So what I am doing actually with this galvanometer, so what I am doing is I am dividing this resistance, the combination of R and S, as my wish. As my wish, I am just changing this, the length of R and the length of S. So what I am doing, I am actually varying these two as my wish. Okay, I'm adjusting these values so that I get another point. And whenever I get another point, I can say, okay, this resistance is equal to, this resistance is S, this is R, and we just calculate the ratio of this resistances. Then that is equal to P by Q, and from here, okay, I'm sorry, this would be Q here, sorry. And from this P by Q over here, so I'm doing it again in short, that is, if we know the value of R and S, so here we can calculate the resistance ratio, and from there we can easily calculate the value of the unknown, that is the value of the P, if we know the value of Q. So what I am doing is I am adjusting R and S as my wish, and we are getting a point where there is no current flow to the galvanometer. So in that particular situation, I can say R and S is having a resistance in ratio, so that that will be equal to P by Q. And if any one of this is known, then the other will be also known. So that is the logic behind this practical, which is obviously, I talked about this in your theory class. Again, I am repeating it a bit. So this is the logic behind this. Now, how to measure the value of this S and R? Suppose, as I told you earlier, this is of 1 meter. This total wire length is 1 meter or 100 centimeter. Okay, and this wire has a particular cross-section area. It has a particular cross-section area. So I'm writing it over here, CSA. It has a particular cross-section area, this wire, fixed cross-section area. So suppose if we measure the length of R, let the length is L, which we can measure from the scale over here. Okay. So if we measure the length of R, then we can easily say R is having a length of L, and the rest part will have a length of obviously 100 minus L in centimeter. Okay. So this part will have a length of 100 minus L, and this part will have a length of L, which we can easily measure from the scale over here. Okay, there will be a scale or a ruler to measure the length where we are getting another point. Okay, so I got this length of the wire. Okay, so I can write the resistance R is equals to, by the formula, rho L by A. Okay, you know this. I have also learned this in class 10. So I'm not going deep into this formula again. So R equals to rho L by A, which we already know. And from here we know the value of L. Okay. And S. S has a resistance of obviously rho into 100 minus L by A. So this is the value of L. If we just know the value of L, and obviously 100 minus L will also be known to us. So this part is only known, this 100 minus L, and only L is known. So what I need to do is calculate the ratio of R and S. So we just calculate the ratio of R and S. We can easily say that we have a ratio of rho L by A divided by rho 100 minus L by A. Okay, for telling you about rho, you already know. Rho is actually the resistivity, that is resistance per length of this wire, which is also constant, because if you just take a sample of this wire here, so this length of wire will have a resistance, and again if you just take a sample from here, this will also have the same resistance if the length is same. Okay, so that is resistivity I'm talking about. So whatever, leave it. So this is resistance per unit length. Obviously per unit cross section area, that is different thing, we have already learned it. I'm not going deep into that. So ultimately if you know L and 100 minus L by this ratio, see this cancels out. What we are left with is this. Okay. Okay, I'm gonna rub this part so that I continue the calculation and the explanation. So, as I was talking about, we have the ratio of R by S. So obviously, P by Q equals to R by S. So R by S is equal to L minus 100 minus L. Now, if any one of them is known, any one of the top resistances, that P and Q over here, if any one of them is known, like we have considered Q to be known, then I can easily calculate the value of P over here from here. Okay. So I can easily write that P equals to Q into L by 100 minus L. So we need a known value of resistance and L. So by this information we can easily calculate the value of the unknown resistance. So what is the gist of this practical? So the gist is we have a resistance over here. In P we have a resistance known. In Q, we have a wire like this, power supply like this, sorry, okay, we have a wire. This is the combination of R and S and a galvanometer. So what we can do is we can switch this pointer wherever we wish, and accordingly we can divide this length of the wire into two parts, R and S. Okay, so as we have we can vary the R and S as our wish, so that we will ultimately get a point where there will be no current flow through the galvanometer, and in that case we can say that okay, this equation will be maintained, and if this is maintained, from the value of L we can get this L, we can get 100 minus L, easily calculate that, and if we just get this, and if any one of them is known, the other will be known also. So this is the logic behind this practical, and that's it.